So welcome to lesson 6 from my refresher course. Today we're going to be talking about sequences and series. So let's have a quick chat, just talk briefly, a quick warm up about what we mean by sequences and series, and in particular what we mean by arithmetic sequences and geometric sequences. So a sequence is just going to be a list of numbers that goes on forever, right? So you start off with some starting number, which we usually call A. So in this case here, it would be A is equal to 3. And then it would be a list of numbers that just keeps going and never stops. Right? Now, why would we want this? Well, there's reasons, it's kind of about, algorithms, computer science, and, making kind of predictions about the future and things like this. Okay. Now, when we have that, we have let me give you an example of a sequence here. We could have a sequence all of the number 1 that's going on forever and ever and ever. Or we could have a sequence where it's just we're just going to count up forever and ever and ever. Or we could have a sequence where we just start with 1, then we pop to -1, then we pop to 1, then we pop to -1. So we just alternate between two values, for example. So there's many, many different ways in which we could create different sequences. And so what we want to begin with is a rule for generating sequences, okay? And the first one and the easiest one is the arithmetic sequence, okay? So what we have is we have a starting number, which we could call, let's say, for example, 3. And then we have a number which we call the common difference, which is just a number that we add to 3 to get the next number on the list. The 3, 5, 7, 9, 11, 13, and we go on forever. Another way to make a sequence is what's called the geometric sequence. And this time we have an A, let's say, equal to 3, but we have this number which we call OR, which is the common ratio, which let's set that equal to 2 as well. And then A is our starting number, but to get our next number, this time instead of adding, we multiply, right? So we get 6, then 2 times 6 is 12, then 2 times 12 is 24, and so on. We just keep on going. So there's nothing really special about arithmetic or geometric sequences. What's special is just sequences, right? There's lists of numbers that go on forever, and we need a kind of a rule to generate them, okay? So if we look at these examples here, can we say if they are arithmetic or geometric? So let's start with the first one. So have a think about this. It's a sequence of these 3 dots. They just mean that they'll go on forever, okay? So what do we have here? We have a starting number, which is 3. And we have, if we go from 3 to 7, well, we can add 4 to get there. But what about the next jump? And we see that's also 4. And we see the next jump is 4. So I'm going to say that this is arithmetic. And the next number would be add 4 will be 19. And the next number would be add 4 will be 23. Okay. Now this one here, we start with 2 and we can add a 4 to get to 6. But if we add 4 again, we get to 10, we don't get to 18. So this is not arithmetic. But another way to get from 2 to 6 is to multiply by 3. So 2 multiplied by 3 is 6. And 6 multiplied by 3 is 18. And then 18 multiplied by 3 is 54. So this one is geometric, okay? So I didn't mean to underline that one. So arithmetic and geometric. Now the next one, okay, so the numbers count down. Our starting number is 20. And then we go down to 17. So how do we go down to 17? Well, that's like subtracting 3. And then we go from 17 down to 14. So that's subtracting 3 again, and then subtracting 3. So what we have this time is A is equal to 20. And the common difference is actually a negative number. It's -3. So if we 20 minus 3, minus 3, minus 3. And the next two numbers here would be 11 minus 3 would be 8. And 8 minus 3 would be 5. Okay. And then this one here, it's saying, is this arithmetic or geometric or neither? And if we could add 5, but then it doesn't work with the next one. We could multiply by 2, but then it doesn't work with the next one. So this is neither, right? This was The last one was arithmetic, and this one is neither. Okay, so it gives you an idea about these two main sequence sort of types that we look at. Okay, so a sequence is an ordered list. So what we're going to have is, you see this one, this two. So we're used to what are called superscripts when you write the script. Script is just writing. So super means like basically above, right? So if you have like a squared or a cubed, we understand this is multiplication. But in maths, when we say A1, A2, A3, this is a counting number. This is the first one. This is the second one. This is the third one. To say something is an ordered list just means it's a list, but the order is important. So there's a first one, there's a second one, there's a third one. Okay, and just these are called ellipses. It just means it goes on. Okay, it just keeps going. Okay, it never ends. Okay, but what we want is we want a rule to generate the nth term in a sequence. Okay, and we what these are the two core patterns that we're going to look at, which are arithmetic sequences and geometric sequences. So what we want is a rule that allows us to jump to a certain place in the sequence. Okay, so let's have a look back here. See, I got to this 23 by first having to write the 3, then add a 4, then add 11. So I had to get all of the previous ones before I could write down the 23. So to get the sixth one in the list, I had to write down the previous 5. I don't like that. That's too much work. I'd like to have a formula that I can use that can allow me to jump straight to number 6. Okay. So what formula is that? And oh yeah, and by the way, just before we go on, I just want to define what this means. Let's say this is a series. Starting number 1, the common difference is 2. So 1, 3, 5, 7, 9, 11. So like we generate the terms in the sequence like this, okay? But if we were to add them up, let's say if we were to take 1 plus 3 plus 5 plus 7, that would be called the series. Okay, so the sequence is the list. The series is the sum of the sequence. Okay, it's just a name, but sometimes you just want to write down the list, and you might want to get it to this particular number. Like T5 would be the 5th term in the list. We also call it A5, right? So it doesn't really matter. Sometimes you use different symbols, okay? But S5 would be the sum of S1 plus, A1, the first number, A2 plus A3 plus A4 plus A5, okay? Okay, so brilliant. So let's have a look at what we have. So on the next page, let me add here. So this is what we have in the tables, which you can take into the exam. We have these formulas here. On the first side here, we have the arithmetic sequence or series. This is to get us terms in the sequence. And on the next column, we have for the geometric sequence. So this is for the sequence, and then this one is for the series. Okay, so this is to get terms in our sequence, the Tn, and to get the sum up to that, to a specific term, that's the formulas underneath. And I guess we don't need to worry about that formula for ordinary level. We don't have to worry about that formula. Okay, so we'll come back and we'll keep sort of referring to this. Okay, so let's continue. Okay, so right, so if we have an arithmetic sequence. I'm going to write down an arithmetic sequence here. Now, the first number in the sequence is 4. So A is equal to 4, and D is equal to 5. Okay, and then we have the general form, AN is equal to A plus N minus 1 times D. Okay, so let's go ahead and write. So the first number is 4, and then the common difference, so the number I have to add is 5. So 4 plus 5 is 9. 9 plus 5 is 14. 14 plus 5 is like 19. 19 plus 5 is 24. And we keep on going, okay? And this here is the first number, A1, A2, A3, A4, and A5. Well, let's say we wanted to go straight up to A5. Okay, so let's write what is A5, and we could use this formula here. So that formula says that it's A, the first number, 4, plus n minus 1. Now, n is 5, right? Because we're talking about the fifth number in this, so n is 5. It's n minus 1, so that's 4 times the gap, which is 5. So that's 4 plus 20, so it's 24. So this formula allows us to just jump right up to the one that we want. This is the kind of things that we want in mathematics, which is a way to like quickly get to places and quickly get what we want, right? Now, it also makes a whole lot of sense, right? Because you see, in order to get on from starting here to the 24, I have to take the 4 and I have to add on the gap, which is 5, but I have to add it on 4 times. 1, 2, 3, 4. You see? So that's the 4 plus 4 gaps. And we can also make a graph of this, okay? So what we're going to have here on this axis here is like 1, 2, 3, 4, 5, 6, 7. So these are the counting numbers. This will be for n, okay? So I can label this axis n, and then this axis I'll label an, and then we see that it's we'll have a look, like it's like 4, 9, 14, 19, 24. So it just goes up. Basically, it goes up like a straight line, basically, okay? Something like this. Now, so we have so we have this time a new arithmetic sequence. A is equal to 7 and D is equal to 3 in our arithmetic sequence. And then our formula is an is equal to a plus n minus 1 times the d. So this is just this formula here. In the table book, they call it tn. But as I said before, like a's and t's, these are labels like, like we shouldn't, these work for us, right? These are our tools. So we can just name them whatever we want, right? Like we shouldn't be like, oh, wait, is this a different thing? Or, it's just whatever we happen to be calling it. And then the question is like, okay, well, that would mean since A is equal to 7 and D is equal to 3, then this is the formula here, okay? And then this tells us that like A10, how do we get A10? So instead of having, we could start with 7 and we could write like 7 plus 3 is 10, plus 3 is 13, plus 3 is 16, plus 3 is 19, and go on until we got to the 10th term or the 50th term, See, I can do it it's plausible to do this for the 10th term. Let me do it 1, 2, 3, 4, 5, 6. So I just needed a 7, 8, 9, 10. 34 is what the 10th term is, but I'm definitely not going to do it for the 50th term because it's just ridiculous, okay? So, okay, how do I do that? Well, A10 is equal to 7 plus 10 minus 1 times 3. In other words, the first number plus 9 gaps. And it ends up being 7 plus 9 times 3 is 27, which is like 34. So that one is what we got already. But what about A50? Well, that's going to be 7 plus 50 minus 1 times 3. Okay, so 7 plus 49 times the 3. And then if you want to know what 49 times 3 is, just say 3 times 50, which is 150, and subtract 3, because it's not 50 threes, it's 49 threes. So 50 threes minus 1 3. So that'd be 147 plus 7 would be 154. Yeah. So that's A50. And then what we can also do is, we could always check that the difference always stays like between terms is always equal to D in an arithmetic sequence. Okay, so this time we're like, for an example like this, yeah. So this time we're given the question kind of backwards. We're told that A is equal to 12, and we're told that D is equal to minus 2. So then we can go ahead and write the formula. AN is equal to 12 plus n minus 1 times minus 2. We could even write that a little neater. 12 minus 2 times n minus 1. Okay, and this time we're not told, we're just told that somewhere on the list we end up with a -8. Now I'll tell you where that is. You're not going to like it. 12, 8, 10, 8, 6, 4, 2, 0, -2, -4, -6, -8. And this is the first number in the sequence, the second, the third, the fourth, the fifth, the sixth, the seventh, no, the seventh, the eighth, the ninth, the 10th, the 11th. So the 11th term on the list is equal to -8, -8. Okay. But the question is actually like, what value of n, like which term in the sequence will give us this -8? So what I simply do is I just say 12 minus 2 times n minus 1 is equal to -8. Okay. See what I'm saying? So what I'm saying is that an is equal to -8. Well, what is an also equal to? It's also equal to this thing. So take that thing and set that equal to -8. And you see, we only have one unknown. And then I'm going to bet you that this is going to be 11. Okay. So let's multiply it out. 12 minus 2n minus 2 is equal to -8. So I have now got a 12. This is a 12 minus, sorry, I did that wrong. +2. Okay. So we have a 12 minus 2n minus 2 minus 1 is +1. And you always make that mistake when you sort of are not actually in the moment. You're not actually looking at you're thinking ahead a little bit. And I just sort of made a mistake with a minus sign real quick because of that. So this is 14 minus 2n is equal to -8. And that means that -2n is equal to -8 minus 14. And that means that -2n is equal to -22. And this means that n is equal to -22 over -2. And that means that n is equal to 11. Okay, so this is much quicker than writing the numbers in a sequence. Maybe it didn't seem like that for that example, but if we were at the 50th term in the sequence, then it would be. Okay. Okay. Now, for the next type is the geometric sequence. So for the geometric sequence, what we have is a starting number. This time it's 5. We'll call it a is equal to 5. And then we're going to have this number, the common ratio, which is going to be, instead of a number that we add on to 5, it's going to be a number that we multiply by 5. So our sequence will start with a 5, then it'll be 10, then it'll be, multiply that by 2, it'll be 20, then 40, then 80, then 160. You can see these get large quick. 320 by 2, isn't it? 640, then 1280, and we just keep going and go. Okay. Now, if we have a look at this, see this first number is just a. This is just a. And this second number is, well, it's 5 times 2, but it's a times or. It's a times or. And the third number is the previous one, which was a times or, and that's now just multiplied by or, so that's a or squared. The next one is a or squared multiplied by or, so that's a or cubed. The next one is a or cubed multiplied by or, so that's a or to the power 4, a or to the power 5, a or to the power 6, and so on. So what you see is this is the first number in the list. This is the second, this is the third, this is the fourth, this is the fifth, this is the sixth, this is the seventh, okay? And what we have is, if we look at them all, oof, sorry, again, a bit messy. What you see is that this number, the 1, the 2, the 3, the 4, that's n. And this is, you see, this is 2, and this one is 3, and this one is 4, and this one is 5, and this one is 6. So you notice that that number, the power is always 1 behind the counting number. See, 3, 2, 4, 3, 5, 3. So this is a or to the power of n minus 1. That's why it's that, right? So it's an is a times or, and it's n minus 1. So it's just take the starting number and then multiply it by or. Just like if this is a7, then take a and multiply it by or 6 times. Or if it's a10, then take a and multiply it by or like 9 times, okay? And these things here, the numbers either get really, really huge or they get really, really small, okay? So an example might be, let's say we start with the number 2, a is equal to 2. And this time, let's make or a half. So the first number is 2. The next number is 2 by half. It's 1. The next one is a half of 1. It's a half. The next one is a half of a half. It's a quarter. The next one is a half of a quarter. It's an 8. The next one is a half of an 8. It's 16. It's the next one, and so on. They get smaller and smaller and smaller like this. So they either blow up, they either fly up like this, or they go down, basically. And then you can have a weird special case where like a is equal to 1. Let's say a was equal to, think of a number like 7, and let's say or was equal to 1. So we would have 7, and then 7 by 1 would be 7, 7, 7, 7, 7. So when or is equal to 1, then they just stay flat. But when or is greater than 1, then they go up. And when or is greater than 1, less than 1, then they go down. Okay, brilliant. Okay, so if we want to tell the difference between an arithmetic sequence, this is just a quick kind of refresher. For arithmetic sequences, the differences always have to be constant. But for geometric sequences, the ratios are constant. So when you have to divide subsequent terms, and then you see that they're like this. And then yeah, so there's things like if you see a sign change, you see this one here, it's like positive, 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 and then it goes negative. So this tells me that the D is a sort of a sinking number, like it's bringing it downwards, right? But here you see the way that changes from plus to minus, from plus to minus to plus to minus. That tells me that my or is a negative number, okay, because it's flipping the sign each time. Okay, so or is less than 0 here. Okay, so and it's equal to, actually or here is equal to minus 1/3, isn't it? Because 9 multiplied by minus 1/3 gives me minus 3. Minus 3 multiplied by minus 1/3 gives me minus by minus is plus. 3 by a third is 1, and so on. Okay, and then there's things like, one of the nice things about this thing, I guess, is that you kind of apply it to a real kind of situation. Like an example might be if you're sort of saving money, like you're saying, okay, I put 10 euro each week into a jar, and then, if I was to look at the totals, that's in the jar, I'd see that it's 10 plus 10 plus 10 each time, right? So, and then we know after n weeks, then it would be 10 would give us the sequence. Okay, so we can look at a few worked examples. Let me see what I have here. So the rest of this now is just some worked examples and a couple of quiz. It's not a bad topic. There's not too much to it. Maybe a bit more when we look at the geometric sequences, then it'll be a bit more. So okay, so we start with 50 euro. So our A is equal to 50, and notice how I'm sort of like the things that I kind of write down is just the bare bones of what I need. Tn is equal to 50 plus 15n, and the question is to get T26 and T52. So T26 is equal to 50 plus 15 times 26. Okay, and we work it out. So let me just get the calculator. What was it? 15 times 26. 15 times 26. 300, no. 15 times 26. It's 390. So this is 50 plus 390. 50 plus 390, which is equal to 440. So if you put a 50 euro into if you had started with €50 and you added 15 each time, and you did this for 20, sorry, you did this for, yeah, this is a little weird. Sorry, because we are kind of breaking our formula just a little bit. Let's just have a look at this. So look, let's look at what it's saying, okay? Let's look at what it's saying. So it's saying you start with €50 and you add 15 each week. So for the first week, it's actually, you have 50 plus 15, so you have 65. And these questions are a little bit, what kind of catches you out with these questions is just sort of like, what is our starting point exactly? Now, if we consider 65 to be our starting point, then our formula would be 65 plus 15 times n minus 1. But equally, this formula here also works fine because we can just multiply this out and we subtract minus 15, it comes across, and 65 minus 15 gives us that 50. So both forms kind of work. But we were given this one here, so in the question, so we could just go ahead and use the formula. So it's just a little bit like the way I kind of think about it sometimes is like, if you're watching a football match and then before the striker takes the shot that goes into the top corner, they take a little touch. And the reason for the little touch is just to sort of set themselves up so everything's under control before they launch into what they're actually trying to do. If they don't do that, then they can go badly wrong, right? And it's the same when you do these maths problems in a sense, because like each time you get one of these questions, it might not be possible to just go ahead right that moment and apply the formula, right? You just have to do maybe have a look, make sure everything's okay before you go ahead and apply the formula. And there may be some little bit of something that needs a tweak, and then it will work, okay? And then working out the second one, T52 will be like 50 plus 15 times 52. This was 390, so twice that would be like 7. That'd be 50 plus 780, which would be like 830. Okay. And the totals are an arithmetic pattern because you start off with 50 and you keep adding 15 each time. So that's why it's an arithmetic. Now, one thing that happens is they talk about this in the like geometric sequences in the context of like compounding interest and stuff like that, right? So a question that often comes up, and we'll see where it is, will be something like, let's take this one here. Okay, so let's say they say, you have like an amount of money that's invested, let's say €100 has been invested, and it's being invested at a rate, and we'll give that an I this time for that interest rate, right? Of an interest rate which is like 5%, and this is like per year. Okay. Okay. So what it's saying is that in the first year, we put in €100 into the bank account, and we have an interest rate of 5% per year. And so we're taking this number like 100, and at the end of the first year, the beginning of the second year, we're going to have more money. And how are we going to find out? Well, it's going to be €105 because we've gotten this 5%. But what have we done in particular? Well, we've gotten this 5%, and we realize that at the end of the year, we'll have 105%. And another name for 105% is 1.05. So or is equal to 1.05. So now you see, we've done this sort of nice sort of like my kind of thing is that we've sort of stripped away all of the context. We don't need to see another percentage sign again. We never have to see this I. We don't need to think about our bank balance and all the stresses that brings up, right? That's how questions are often made difficult in maths, is they give you extra information that you don't need, right? So now at the end of the second year, you see this time it's compounding. So we've got like, we're going to clear that off here. So 105 this time multiplied by 1.05. And that's going to be 110.25. So it's kind of like we added on 5 again, but we have a little bit more than that, right? And then we take this 110, and see the way I can just go ahead and just multiply 1 by 1.05, and I get like 115.7625, 115.7625, and then I can take that again and I can multiply by 1.05, and I get 121.5506. And it goes on and on and on. Now, this is going to be annoying. So what we want is a formula to work out. Let's say this is, the first year. So I'll call this A1. This is A2. This is A3, A4, A5, and so on. Okay, so we have A1. So AN would then be equal to A times or to the power of n minus 1, which would be, well, A is 100 and or is 1.05, and then to the power of n minus 100. So we might say, well, what happens after 7 years? N is equal to 7 years. A7 is equal to 100 times 1.05 to the power of 7 minus 1, which is 100 times 1.05 to the power of 6. So in this way, we can actually just jump to that term using that, okay? So in a sense, this is what I mean. It's sort of like just at the start of the question, there's a kind of you just need to do a little bit of tinkering about just to get to that 1.05, right? And then we're good to go to start using formulas. Okay, so now we want to go, for example, from a wordy type of question to be able to get to, like, to be able to get to an equation. Okay, so we're saying that there's we have a bus seat row adds 4 seats each row from the front. A bus seat row adds 4 seats each row from the front. Row 1 has 12 seats. What the hell? What kind of bus is this? Maybe we shouldn't say bus, we should say plane, because I think this is just a bit ridiculous, right? So imagine a plane where it's sort of like, okay, this shouldn't be a plane or a bus. This should be a theater. Okay, sorry. This doesn't make any sense. Okay, sorry, I wrote these last night. So, okay, so this is like, what is it? So here's a screen, and here's the first row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and then what we're going to do is have the same thing, but then in the next row, you see we've got more like that. And then the next row, we got more like that. Okay, something like that. Okay, so what we're doing is the first row, we have row 1 has 12 seats. And then we want to find AN, and we're going to add 4 seats each time. Okay, so we have an A is equal to 12. And if we're adding 4 seats each time, then the D is equal to 4. And then we're able to write down this here immediately. And then we're able to find A20. Okay, so what we have then is, sometimes you can imagine like two lanes. Okay, this is the real world, right? This is the maths pretend world where we can do models and work things out. So we're going along and we have a question which requires like we don't want to go around counting, right? So we want to have a formula to give us the ability to jump just straight away to say how many seats do we need in the 20th row without having to count every one in between. So we jump from the real world into the maths world, and then we can work with the maths, which means applying a formula, and then we can get a result from that one. So A20 then is equal to 12 plus 20 minus 1 times 4. So we can get 12 plus 19 times 4, whatever that is. So that's going to be 12 plus 76. So that's going to be 88. So there's going to be 88 seats in the 20th row. And then once we have that answer, then we can pop back over into the real world again. And you can say, yeah, we need 88 seats then in the 20th row or something. Right. So this here is all the words. This is the theater. This is the seats. This is the all of the real world concerns. Here we're just dealing with A's and D's and AN and stuff like this. So this is what you usually need to do in a maths problem, is just to make sure that you're set up, that you've sort of set yourself up to be able to just launch into a sort of a, you know, a mathematical sequence of statements, like, okay, this implies this, and then equals, yeah, and then get an answer, put a nice box around it. And then, so here we would say, what are they saying? Like, we would say there needs to be, in words, there needs to be 88 seats in that row. Okay. Now, another thing that we can be given is we have an arithmetic sequence, but we don't know what the A is and we don't know what the D is. But what we know is that AN is equal to A plus N minus 1 times the D. Now, how do we know that? Because we're given it. Okay. Okay, so this is AN, which is, now this time we don't know what the A is and we don't know what the D is, but we do know from the first one that when N is equal to 5, A5 is equal to 23. So we have 23 is equal to A plus 5 minus 1 times D. 23 is equal to A plus 4D. And the other thing that we know is that when N is equal to 12, A12 is equal to 51. So we have 51 is equal to A plus 12 minus 1 times D. 51 is equal to A plus 11 times D. So why don't we call this now? I'll just call this one equation 1. And I'll call this one equation 2. And I'm going to rewrite this as A plus 4D. No, I'm going to write equation 1 first. A plus 11D is equal to 51. And I'm going to, the second one, A plus 4D is equal to 23. And see what we've gotten from this here, because we've been given these two sort of like, how would we think about this? Like, we might be in our theater example and we'd be like, look, I don't know who made this theater in the first place, but it's written down here that they did something in an arithmetic sequence. Okay. So the number of seats in a row follows an arithmetic sequence. And then someone says, well, you know what, in the fifth row, remember there's 23 seats. And another person says, well, you know what, in the 12th row, there's 51 seats, and then everybody realizes, oh, we can use this formula that we learned on the Leaving Cert to answer this problem here about how many seats in the theater. Totally unrealistic, but you get the point that you can work backwards to recover back the A and D from the arithmetic sequence. Okay, so the first one gives us A plus 11D is equal to 51, and the second one gives us it was the other way around, but I just labeled them this way. We have a simultaneous equation. So we know that if we have an equation and we only had one unknown in it, then we would be able to solve it. But here we have two unknowns. And in order to solve, so what we want A equals and we want D equals, right? We want the two of those things. In order to solve those two things, we need two equations. So we've got two unknowns, we need two equations. If we have three unknowns, we need three equations. If we have 10 unknowns, we'll need 10 equations, okay? So it's just, you always need the same number of equations as you have the number of unknowns. Okay, so we call this a simultaneous equation, which we haven't covered yet in the refresher course, but that's something that you do in algebra. I believe you would have covered it last year. Okay, and what we're going to do now is I'm going to realize that I can actually just subtract these lines. So I'm going to subtract the second one, means put a minus sign here, put a minus sign here, put a minus sign here. They cancel to give a 0. This cancels to give me a 7D. And this cancel here, 51 minus 23 is equal to, why did I have to pick something? Obviously chose the numbers probably badly, did I? So this is going to be 28. Yes, 28. Okay, so not chosen badly. 7D is equal to 28. D is equal to 4. And then well, I can just go ahead and say, take the second equation, a plus 4d is equal to 23. I just put those minus signs because I was subtracting, but before that it was a plus 4d. But it's going to be a plus 4 times 4 is equal to 23. That's a plus 16 is equal to 23, which tells me that a is equal to 23 minus 16 is equal to 7. So a is equal to 7, and then d is equal to 40. And now we have to find a 50, so we can just use that formula. A 50 is equal to a 7 plus n minus 1, which is going to be 50 minus 1 times 4, which is 7 plus 49 times 4, which is going to be, well, 49 times 4. What's that? Well, I just say it's 50 times 4, which would be 200, minus 4. So it's 49 fours is the same as 50 fours minus 1 4. So that's going to be 196 plus 7 is going to be 203. Okay, great. Okay, so the other thing might be you are sometimes given something like this, okay? And you might like go, someone, it might be the question which is about sequences. And it's a question about sequences because you see these ellipses and oh, that's the sequence stuff or whatever. And then you might want to say, well, for sequences, like there's arithmetic sequences and there's geometric sequences. Which one is this? And like what I would say is like, there's some indications. Like you always want to be able to kind of glance at something and kind of say, like rule something out maybe in the first place. And I would say like there's no way this is arithmetic. There's no way this is arithmetic because like where's this decimal coming from if it's arithmetic? Like if it was arithmetic, I'd add on 50 here, but like where's this decimal coming from? So it must be geometric, right? If it's anything, like if it's like a sequence doesn't have to be arithmetic or geometric, right? There's lots of different ways like that you can make sequences, like infinite number of ways that you can make sequences, right? But sorry, but like on the even cert, they only give you arithmetic and geometric sequences. They may give you another time, but they, you know what I mean? They wouldn't say like you wouldn't be able to name it, right? It would just be some rule or something that they've given you or whatever. Okay, so in this, if we want to recover basically what is if we suspect, which we do, that this is a geometric sequence because we know it's not arithmetic, how do we get the or? Like the A is obvious. The A would be 1000 because it's just the first number in the list. But how do we get that or? And what we're doing is we take the consecutive terms. So 1050 divided by this ends up being 1.05. Okay, so that's what we would have to multiply. So this is like, we kind of think this is, if it's geometric, this is our or. But of course, we have to check this next one. And let me just go over here. So that was what was it? 1102.5 divided by 1050, and we get 1.05. So we see that's the same. This is like multiplying by 1.05, and this is multiplying by 1.05. Okay. So we have the or is equal to 1.05. So you're dividing consecutive terms. It could happen. Do you know what I mean? Like it could happen that that the next number isn't like that, right? Or whatever. But if we're only given three numbers and we suspect it's either arithmetic or geometric, then what we're going to do is we're just going to like, okay, we see 1.05 here, we see 1.05. It's a geometric sequence. Okay. So we're done. Okay. And then as soon as we have it, then we're like, figure out, estimate or from consecutive ratios. Now we have like, a to the power of, sorry, I've made a mistake here. Should be down here. So now we can write down an is like 1000 or to the power of n minus 1. So this is 1000 and the or is 1.05 to the power of n minus 1. So this is our rule. And now we have to use our rule. Okay, so that's how these ones always end. It's like, get the A, get the or, like write down the rule, and now use the rule. Okay, so it's going to be 1000 And that's like kind of, it's one thing I like about this section is just how procedural it is, right? It's just how much it's like, do this, do this, do this, do this, do this. These questions are very often like that. Like, and maths questions are very often like that. And once you see that, you have to do a bunch of examples. Like the kind of rule is like, if you've done 4 years of exam questions, like not exactly, but if you've done 4 years of exam questions, you've kind of seen it all, right? You've seen all of the different variations that they have of like asking a question, right? So, all right, and then you would work that out, and then you would get what it is. Oh yeah, now this is another one that they like to do, and they're called like here we're calling it a threshold question, which is probably not what. So imagine you're in a situation where you're like, I want to buy a bike and the bike costs so much money and I'm able to save this much. Basically, when the bike costs €300 and I can save €12 a week, or you know what I mean? Like after how much time are we going to be able to get that, right? So what we do, like so basically it says when does the first total reach at least this €101? So we have something like, we have like €5, we can say we have €5 in our bank account or in a piggy bank or whatever, and then we can put like €2 in extra per week. And when will we have €101, which is enough money for something? And what we're going to do, it's just a little tiny trick. But what I'm going to do is I'm going to say AN is equal to 101. Okay, I'm going to say AN is equal to 101. Now I've written something down here which is actually, strictly speaking, not true. Why is it not true? Well, let's have a look at our list. 5, then we add 2 on. So we say this is our A. Our A is 5, right? Our D is like 2. Okay. So 5 and then 7 and then 9 and then 11 and then 13 and then 15 and then 17. And then we keep going all the way down the list. And, I'm not sure we land on 101. We probably will. But, let's say we don't know that 101 will happen to be on the list, like here, right? So if I say AN is equal to 101, I may end up getting N as some decimal number, okay? And if that's the case, we have to look at the decimal number. Like, let's say it's like 10.5. Then, like, so let's say it's going to take 10.5 weeks to get up to €101 or something like that. Then it's going to take 11 weeks to get up to, because we were counting the weeks in whole numbers. Okay, so sometimes you'll have to, whatever number that you get out, you'll have to either round it up or round it down. So we're going to say AN is equal to, so that means that 101 is equal to 5 plus N minus 1 times 2. We bring across the 2. 99 is equal to 5. No, we don't bring across the 2, sorry. We bring across the 5. So that means that 96 is equal to N minus 1 times 2. 96 over 2 is equal to N minus 1. And then 96 over 2 is 48. So that means that N is equal to 49. So it happened to be, so after 49 weeks, we get up to 101. So we can say this is how long we need to get to. Now, if this was 100, then let's try it again. So let's say we didn't want €101, we wanted €100. So then 100 was equal to 5 plus N minus 1 over 2. Bring that across. 95 is equal to N minus 1 times 2. 95 over 2 is equal to N minus 1. And then this tells us here that 95 over 2 is equal to 47.5. Right, 47.5 is equal to N minus 1. So 48.5 is equal to N. So what's that saying? After 48.5 weeks, we're going to have €100. But in this thing, like we're putting in €2 each week. We're not putting in €1 for half a week. So 48.5 doesn't make sense. So the number that we have to say N is equal to 49. Okay, because on the 48 week, we only have €99. And so by the 49, we have 101. So in order to have €100, then we would have to do this for 49 weeks. So it's the same answer as that one, okay, as the number of weeks to clear that threshold, okay? So those threshold questions, you just have to make sure that you're you round up or round down. And that's, you also have to look at it and be like, wait, am I rounding up now or am I rounding down now? Usually, if you're there, you'll probably just lose 1 mark out of 10, something like that, for maybe rounding down when you should have rounded up. Okay, so take a moment to just have a look at the ones here and then classify the following. And then, sorry, I'm just yawning, sorry. So classify, so the first one, A is 7, A is obviously 3 here. So we want to classify the two of them. And then we want to find the common difference or the ratio in each case. And then finally, we want to state AN concisely. So I'll just give you a moment there just to have a look at that. Okay, so from the first one, if we jump from here to here, let's just start with arithmetic and see if it works. So what would our D be? Well, this would be a -6. Now, does to get from 1 to -5, yeah, that's also minus 6. So this is D is equal to -6. Then we have that AN is equal to A plus N minus 1 times like D. So it's going to be 7, plus N minus 1 times -6. So it's going to be 7 minus 6 times N minus 1. And then the second one, in order to go from 3 down to -6, we have to go down by -9. But going down a further -9 from -6 doesn't bring us to 12, so it's not our arithmetic. So if we want to go to 3 to -6, we'd have to multiply by -2. And then to go from -6 to 12, we'd have to multiply by -2 again. So this is geometric, and this is OR is equal to -2. And then AN is equal to A times OR to the N minus 1. So we have that AN is equal to A3 times -2 to the power of N minus 1. Okay, so have a look at this one here and see if you can work out A15 and the next one, smallest n with AN less than 0. And then for the geometric cases, find A8 and A5. And then once we finish this, we'll finish up. Okay, so let's write down our, let's go back to here and quickly get our equations. Put them up here at the top. These are our two equations. Okay, so first one, and see where to just, I've been using the AN. Okay, so there's no difference. Okay, it's just the name that they give it. Okay, so for our first one, then this means that AN is equal to -8 plus N minus 1 times 5. And that will tell us that A15 is equal to -8 plus N minus 1 times, sorry, plus 15 minus 1, which is the same as 14 times 5. Okay, so the next one is, it's arithmetic. So this is going to be, let's just write it down. So it's going to be an is equal to 90 plus n minus 1 times minus 3. And this is going to be 90 minus 3 times n minus 1. And we're going to say, like, what's the smallest n with an less than 0? And what I'm going to do is just say, well, look, let's just set an to be equal to 0. So I say set that to be equal to 0. Okay. And we're going to see what n gives us that. What value of n will give us that. So 90 is equal to 3 times n minus 1. So this is telling us that like 30 is equal to n minus 1. So this tells us that 31 is equal to n. So what is this saying? It's saying when n is 31, then we have that an is equal to 0. But that's not what we were asked. We were asked when is a1 less than 0. So that means n has to be equal to 32. Okay, now if you see what's happened here in this argument here, like, I've started with this, I've said this, like this was not the correct thing to say. And then we get down to n is equal to 31. Then below I've got n is equal to 32. I'm kind of skipping some stuff. It's not perfect, perfectly sort of written, but it doesn't really matter, right? Like it's clear what your argument is saying. It's clear what you were saying, right? So, you can't leave out too much. We might want to add a sentence here. So, that is for when, an is equal to 0. So for an to be less than 0, that's what we're leaving out. We're leaving just in between kind of text out, which is kind of like, it's okay to do that. So like to an extent. Okay. So you'll see when you do questions, like you'll be able to gauge it, right? Okay. So 2 to the power of 0.5 to the power of n minus 1. Find A8. So A8 is equal to 2 times 0.5 to the power of n minus 1 is to the power of 7. And then the next one, A5, this is going to be A, which is 81 times minus 1/3 to the power of n minus 1 to the power of 4. That would give us those two. So quick recap, then we looked at the arithmetic sequence, which had the constant difference, and this was the formula. We looked at the geometric one with the constant, right? Sorry, this is a mistake. Sorry about that. Should be here. So the arithmetic sequence, the geometric sequence with a constant ratio. Then we had some, some examples with like sort of saving things and then like compound interest to give examples of like how we could be using arithmetic sequences and geometric sequences. Okay, so that's it for today. I will send you, I'll send you a video later, a link later with this, and then an hour before the call tomorrow, then I'll send the refresher. I'll send a mail for a reminder for the call. Okay, so have a nice evening, and then I'll see you tomorrow.